Yes, hello everyone. My name is Aleksandr. I'm from DESY, Hamburg, and thanks a lot to the organizers for setting up this amazing conference and for the invitation. And yes, my talk will be devoted. Okay, why is it not full screen? Okay, 1 second. Yeah, okay, now it's full screen. So yeah, it will be devoted to the Relaxion mechanism, which is not very different from the usual axion. It's just a modification of the mechanism which addresses the Higgs mass hierarchy problem in the standard model. And most of the talk will be based on some recent works which were done in collaboration with Geraldine Servant. So the outline of the talk is the following. The first part will review the Relaxion mechanism itself, whereas in the second part, I will focus on our work where we discuss the role of quantum fluctuations during the inflation and during the relaxation process. And we describe the stochastic effects due to these fluctuations, as well as I will ask questions such as, can the Relaxion be the QCD axion, or in other words, also solve the strong CP problem, as well as can the Relaxion explain the dark matter? Let's start with the review of the mechanism. So, as it was discussed, axion-like particles or similar light scalar fields play an important role in cosmology. They have a wide range of applications, including strong CP problem, dark matter, dark energy, inflation, etc. And axion is perhaps the most well-motivated candidate. It provides a dynamical solution to the strong CP problem. So as a reminder, the standard model Lagrangian allows for such a term, which for non-zero value of theta bar violates CP symmetry. However, experiments on measuring electric dipole moment of neutron put strong bounds on this quantity. It should be less than 10 to the minus 10, which implies that apparently there is no CP violation for some reason in the strong sector. And the role of the axion is that it appears as a Goldstone boson of an additional axial global U1 symmetry and couples to this anomalous QCD term. And effectively, this means that the theta parameter is promoted to a dynamical field variable, which can dynamically readjust itself to the minimum energy configuration. And as these authors have shown, the potential of the axion, which at low energies has the following form, is indeed minimized very close to the CP conserving value. And this way the axion dynamically relaxes to a CP conserving configuration. Now, the focus of this work is the Relaxion and how it addresses how it explains the smallness of another parameter in the standard model, namely the Higgs mass. So, as we know, the Higgs mass is sensitive to UV physics, or in other words, if we think of the standard model as an effective field theory with some cutoff scale lambda, then the mass of a scalar field much larger than the cutoff scale is unnatural. And of course, possible explanations to this smallness, which do not involve anthropic arguments, are usually based on extension of the symmetry group of the standard model, such as supersymmetry or composite Higgs models. However, there are also dynamical solutions which gained some interest over the recent years, where the smallness is explained by cosmological evolution in the early universe. And the Relaxion is one of them, which was proposed in 2015 by Graham, Kaplan, and Rajendran. But there are many other similar ideas as well, and few of them I mentioned here. So what's the basics of the mechanism? Essentially, in this case, the Higgs mass is promoted to a dynamical variable, which is controlled by the wave of this field phi, which is called the Relaxion. And so the Higgs mass takes the following form. Lambda squared is the naive expectation. for the Higgs mass. And then we have this term where G is some small coupling between the Higgs field and the relaxion. And so this generates a rolling potential for the relaxion, which is shown here by this red line. And it allows the relaxion to dynamically minimize the Higgs mass squared. Of course, we don't want this to continue for a very long time. We want the relaxion to stop near a negative but small value, around 88 GeV squared. And for this, there's the second important ingredient in this mechanism, which is the Higgs-Wave-dependent relaxion barriers, which can allow the relaxion to get trapped at a fixed field value. So yes, so this is if one compares this with the usual axion, in the usual axion case, there is only one minimum because it's just a cosine potential, and we don't have to worry about that the field ends up in that minimum. However, here, as we can see, the correct minimum is only metastable minimum. So we have to make sure that the field does not overshoot and gets trapped in a particular minimum. And in other words, there should be a strong friction that the relaxation exhibits. And the simplest way to engineer this is to assume that all this relaxation process takes place during inflation. And during inflation, the dynamics of the relaxation is governed by slow roll. So it satisfies the following equation. And importantly, the velocity of the field tracks the slope of the derivative of the potential, which means that based on this equation, the relaxation will stop at the first minimum. And this will be important for us. Near the first minimum, this condition should be satisfied. So lambda b denotes the height of the barriers at the final minimum. And in order for the local minimum to exist, if one takes the derivative of this expression, one can check that the barrier height should be at least equal to this quantity. Okay, maybe a few remarks about this part. Of course, you might wonder, is the potential unbounded from below? Of course, that definitely is not the case. It's just that for our qualitative discussion, it's sufficient to approximate it as by this linear slope. In reality, it's going to be most likely some larger cosine with a larger period. So, and also one may wonder how comes the field range exceeds this the period of the field. And this one can achieve if one has multiple axions by taking which are mixing with each other. It's similar to the talk that was given on Monday, and this way one can extend the field range for the relaxon. So there are two important cases for the relaxon mechanism. One is the QCD relaxon model, in which case the Higgs-dependent barriers originate from the QCD anomaly. And in that case, we know that the barrier height depends on the Higgs wave via this equation. So it's the proportional to the third power of the QCD confinement scale and the mass of the U quark, which is proportional to the Higgs wave. Yeah, in principle, this is a more minimal scenario. However, as I will show in 2 slides, it leads to the issue that the relaxon no longer solves the strong CP problem, and in fact, it generates order 1 theta angle because of the presence of this linear slope. The alternative scenario is to assume that the barriers, the Higgs-dependent barriers, originate not from the QCD sector, but from some hidden gauge group. And yeah, in that case, lambda b is also a free parameter, and we should assume that the strong CP problem is solved independently, maybe by some other axion or yeah. A few words. So. How large cutoffs can be explained in this framework? It turns out that at most around 10 to the 9 GeV in this model at least. And the reason is that there are several constraints that the relaxon should satisfy. One is that we assume that the relaxon sector does not backreact on expansion rate during inflation. So its energy budget should be subdominant. And this is this condition. When the second condition is if we want the dynamics of the relaxon to be governed by the slow roll equation, which I showed on the previous slide, we have to require that the slow roll of the field within unit Hubble time should be larger compared to the random walk due to Hubble fluctuations during inflation. And this condition is called classical bits quantum condition, and this is something that we are going to relax in this work. However, if one assumes these 2 conditions, then this implies that the Hubble scale should be essentially in this range. And then if one, of course, eliminates the Hubble scale, one can see which parameter space the relaxon can live. And I show it here. On the horizontal axis is the cutoff scale of the theory of standard model. And on the vertical axis is the coupling, G, between the relaxon and the Higgs. And it turns out that the relaxon can live inside this white triangle. As you can see, the values of G are very small, but because it's assumed to be an axion-like particle, it's technically natural to have small couplings for the relaxon. And now coming back to the QCD axion. So the reason why it doesn't work is because of the linear slope. So if one computes the locations of the local minima of the relaxon potential, so we just take the derivative of the potential and say it's equal to 0. From this, it follows that theta bar is equal to arc sine G lambda cube F over lambda B. So if the slope was not there, so G was 0, then this would be essentially 0, and 0 is the CP conserving value. However, when we have the slope, and I just mentioned in the previous slide that the final value of lambda B should be of order of G lambda cube F. So this term is actually of order 1. It means that the minimum, because of this linear slope, is shifted from the CP conserving value by order 1 angle. Yes?
So basically, you start with hierarchy problem. You want to solve hierarchy problem because you have uncontrolled contribution. Now, in order to solve that, like you are adding one field in which, let's say, mass of the Higgs depends, but itself that field, why it is protected?
Sorry, can I say the last part again?
That field itself, why that field is protected from corrections? Because itself, this field will have now hierarchy problem.
Well, I think, but this field has approximate shift symmetry, so then it's protected from corrections.
No, it should, like that shift symmetry should be broken by topological susceptibility, some Chern-Simons form, or as soon as you add like this extra violating term, like its protection is gone completely.
Saying the cure is worse than the disease. That's what it's.
But I mean, I'm not sure I agree with this because, like for usual axion, no, we are not asking why the mass is small.
No, for usual axion, because mass is from, let's say, Chern-Simons pole.
Yes.
And it's like Higgs effect. So shift symmetry is never broken. It's like gauge symmetry. Here you explicitly broke it. So it's not protected anymore from corrections.
Yeah, so this should be it should be a small breaking on top of continuous shift symmetry by construction.
Yeah, but it's scalar. As soon as you explicitly break it, you cannot protect it.
But I can break it with. Yeah, in some sense. So, so if on there is a discrete continuous shift symmetry, and I assume that all these potential terms, they are generated by, so to say, anomalies or this kind of small symmetry breaking effects, soft symmetry breaking effects, yeah, in some sense,
But
then I would.
Sign potential because you can generate with arbitrary Young-Mills sector.
Yes.
But lambda cube, you cannot generate that term from the Young-Mills.
You can essentially. You just need to have it coupled to another. So it's also coming from a similar coupling, but with a larger decay constant. So maybe I should mention. So this G lambda cube phi term is just a Taylor expansion of a larger cosine potential, which I expect is generated in analogy to this one. And because I probe part of it, I approximate it as linear, but one can do this kind of construction. Yeah, I have a backup slide about this in details, but that's the idea. Yeah. Okay. Thanks for the question. Yes. So yeah, what I was saying that essentially, yeah, theta bar is now of order 1, so we can say that this model is excluded by experiments. And the solution that was proposed in the original paper was to somehow get rid of the slope after inflation, and this way reduce theta bar. So this is a bit, of course, non-trivial. Maybe one can assume some coupling between to the inflaton. But if one assumes that this is achieved, then yeah, if the slope decreases by at least 10 to the 10 factor, then this will also reduce the CP violation at the final minimum of the potential. So today the potential will look like this, although during inflation it looks like this. And in this, if one does this trick, then the relaxion would live in this white triangle and can explain cutoffs up to 30 TeV approximately. One can check this. Okay, now let me a few words about the role of quantum fluctuations. And I mean, why did we care about this? Essentially, so if you look at the potential, you can see that the CP violation at the relaxion minima is stronger near the first minimum, but it's much weaker at later minimum. And the reason is that lambda b, because it depends on the Higgs wave, and the Higgs wave grows as the field rolls in this direction, and which means that lambda b also increases. So in a late minimum, this ratio will be much smaller, and therefore theta bar here is much smaller. So the question is, can fluctuations during inflation modify the stopping condition and make it stop much later compared to the first minimum? Yeah. And to understand the role of quantum fluctuations, one has to note that, so we are talking about, the quantum fluctuations during inflation give random kicks to the wave of the relaxon field or any light scalar field. And the reason is that at each time there is a mode which becomes super horizon. And when the mode becomes super horizon, it gives a random contribution to the field expectation value inside the Hubble patch. So as a result, the motion of the field is similar to a Brownian motion of a particle, and can be described either by a Langevin equation or by a Fokker-Planck equation. Yeah, we use the second description. This is the Fokker-Planck equation, and the main observable here is rho, which is the probability distribution of relaxon field wave inside the Hubble patch being equal to phi at time t, and its evolution is governed by two terms. So the first term is drift term, which just comes from the slope of the potential, and the second term is a diffusion term, which is a result of this random kicks. And this equation is well known also in the context of stochastic inflation. And so this diffusion term introduces some effects. For example, one effect is that with time, the distribution function gets broader, as one expects for the diffusion. However, another important effect is that it allows the relaxon to jump over the barriers because of this random motion. Or stated slightly differently, it introduces probability fluxes between neighboring local minima. One can compute how much is the probability flux, and it's given by the following expression. And here, the important ingredient is this exponential term, where B is called the Hawking-Moss instanton. So essentially, B is proportional to the height of the barrier, delta U, and inverse proportional to the fourth power of the Hubble scale. So Hubble scale controls how large is this probability to jump, like this random motion, and that's why it's not surprising that it's given by the following expression. So we can expect that for large Hubble scales, the field will jump over the barriers and stop much later. And this is what indeed observed in our studies. We do two kinds of studies. One is numerical. We just solved the Fokker-Planck equation numerically. And you can see how the wave function of the relaxon propagates, and it overshoots the first minimum for here, which shows particularly large Hubble scale. And it overshoots the first minimum, and it slows down much later. And also when it's in this region, it's not just a Gaussian distribution, but it's a series of peaks. And the motion is governed by the probability fluxes between these peaks. And here you can see in this other plot the velocity of the relaxon field as a function of the barrier height. And the solid lines are from the simulation, whereas the dashed lines are from this analytical method that I described on the previous page. So you can see they agree with each other well. And for different colors correspond to different Hubble scales. So essentially for small Hubble scales, the relaxon indeed gets trapped near the first minima. However, for large Hubble scales, the location where it stops can be much larger and depend on Hubble scale.
So the units of the field
Here, it's in units of 2 pi f, I think, but like No, it's like phi divided by phi divided by f, the decay constant. Yeah, but of course this is just particular choice of parameters. So, but yeah, it's phi divided by f. Yeah. Sorry. F is a free parameter in principle. Yeah, we can take it up to Planck scale in principle.
This is Transplanckian.
The displacement, well, it depends. It can be both subplanckian and transplanckian, depending on what parameter values we use, because there are several free parameters in this game: g, lambda, f. So, yeah. Yes. So, yeah, essentially, to understand when the field stops, one can use as a simple stopping condition just that the requirement that b, this action in the exponent, becomes larger than 1. And this brings us to two different cases of the stopping condition. So lambda b at the final minimum is either going to be given by this expression that we used in the beginning, which means that the field stops near the first minimum, or we have this new regime where the final barrier height is determined by the Hubble scale during inflation, which we assume here to be approximately constant. And this is going to be very important for the QCD Relaxion scenario, because now we will have the freedom to stop much later. So, yeah, and just before proceeding, so in the end, we are left with 3 regimes: the classical bits quantum regime for low Hubble scales. So this is the Hubble scale. For larger Hubble scales, we are in the quantum bits classical regime. And in that regime, we have these 2 cases, which I call QBC1 and QBC2. Your QBC1 is the usual stopping condition. However, for even larger Hubble scales, the stopping condition is completely different, and it's determined by the Hubble scale. And of course, we would like the Hubble scale not to exceed the weak scale, because otherwise the symmetry will be, electroweak symmetry will be restored, and yeah, the mechanism will not work. Okay, now can the Relaxion be the QCD axion? Yeah, so of course, as I discussed, in the classical bits quantum case, this does not work. Because of the order 1 theta angle. So essentially, it only works in this case of new stopping condition. And so for this, we would need two ingredients. So first of all, we would need the Hubble scale to be of order of the lambda b parameter at the correct Higgs wave, which we know is around 75 MeV for the measured Higgs wave. And we would need the slope of the potential, so this term, to be at least 10 to the 10 times smaller than this number. So in that case, the CP violation at the final minimum is consistent with the observations. Yeah. So in this case, so this is our model, and it also predicts a particular value for the Hubble scale. Of course, there is one issue in this scenario which is important to mention. Now the potential is very flat, and the time which is required to reach the final minimum is much larger, which is already large even in the usual case, but here it's even larger. So if one estimates how many e-folds of inflation is required for successful relaxation, one will find that it exceeds a critical number, after which the inflation is unavoidably eternal. And so eternal inflation means that inflation never ends globally. Instead, the universe, every Hubble patch eventually ends inflation and reheats. However, most of the universe is always in the inflation regime. And I mean, this scenario is not excluded. However, it's more tricky to understand it from the mathematical point of view, and which can be summarized in, it's difficult to define measure in this kind of universe. Although there are some solutions, for example, there is scale factor cutoff measure, which seems to solve many of paradoxes which arise in this scenario. So yeah, so one has to say that this scenario will work only in an eternal inflating universe. However, if one is fine with that, then we find that the Relaxion can live in this white region, and you see that the cutoff range which the QCD Relaxion can explain is now much larger. And for the non-QCD model, we have less constraints because we don't have to worry about the theta angle anymore. And in this region, I show with 3 different colors each of this, in which parts of parameter region the relaxion can exist. And in this lower white region, again, relaxation would require eternal inflation. Okay, and now I'm in the final part of my talk. Can the relaxion explain also the dark matter? But before this, let's discuss the interactions of the relaxion. So the relaxion, the main interaction channel for the relaxion with the standard model is via its mixing with the Higgs, which arises from this Higgs-relaxion coupling. Yeah, so one can compute the mixing angle using these formulas and see in which parameter region the relaxion can live. So this is shown in this big plot. Here is the mass of the relaxion against the mixing angle. And different colors denote the corresponding regions where the relaxion can live. In this plot, I also show some approaches how one would detect the relaxion. There are several of them, and they were studied in detail in this paper. So most strong constraints on the relaxion parameter space come from fifth force experiments, which measure deviations of from the gravitational interaction between two neutral particles. Then there are stellar bounds, because the relaxion can be produced in stars, and as well as in the supernova core. Then there are bounds from meson decays, for example, in beam dump experiments, the decays of B and K mesons can produce relaxions, and that's why some region is excluded. And this inset shows, zooms in part of this region to show also the sensitivities of future experiments, which would be able to probe some parts of this region. And the dashed lines show the lifetime of the relaxion in each point in the parameter space. So as you can see, in most of the parameter region, the lifetime of the relaxion is larger than the age of the universe. And this means that it's cosmologically stable. And this naturally brings to the question whether it can be a dark matter field. Yes, and of course we know that light scalar fields are good dark matter candidates if they are produced from the misalignment mechanism. So if the field is displaced from the minimum, then this energy will be converted into dark matter after the field starts to oscillate. And yeah, for the relaxion, there is one peculiarity. Because the period of inflation is so long, this misalignment angle is not really a free variable, but it can be predicted from the final form of the distribution rho. Yeah, in particular, if near the quadratic minimum of the potential, the distribution has the following form. And it leads to a variance of the field. So the typical displacement, which is given by the variance of this distribution, which depends on the Hubble scale and the mass of the field. So if we treated the problem purely classically, the field would be exactly at the minimum. But now, because of these fluctuations, this is the typical expected displacement from the minimum. And then one can use this to compute the Rayleigh abundance. And so now, on the next slide, yeah, I show the results on the next slide. Of course, this is for the non-QCD model, because for the QCD model, the fact that we have to be in a region where the theta parameter is so small, essentially the non-QCD model is is very similar to the usual QCD axion dark matter. So at m mass equal 10 to the minus 5 electron volt, it can naturally generate the correct Rayleigh density. It's a bit less tricky for the non-QCD model, because here the deviations from the usual axion scenario become important. And I show the possible parameter region again in this mixing angle versus mass plane in this plot. Let me explain what color denotes what. So the brown color is the region where, for correct choice of parameters, the stochastic misalignment of the relaxion generates the correct Rayleigh density. There are several curves here, and the different curves correspond to different values of the reheating temperature. However, in all cases, it's assumed that the reheating temperature is low, so it's not above the weak scale. So that because if the universe reheats to a temperature above the weak scale, then the symmetry will be restored, and the barriers of the Higgs of the relaxion potential will disappear. So this scenario was considered by these authors, and what happens in that case is that after the barriers disappear, the relaxon can roll further, and one has to make sure that it gets trapped afterwards. And this displacement after inflation can itself generate a misalignment, enough misalignment for the field to explain the dark matter abundance. And the gray region shows that part of the parameter space where this mechanism works. So just the displacement after inflation generates the correct relic density. And finally, we have this black region. And this is where we combine two effects. So we have both a high reheating temperature and we rely on the stochastic misalignment during inflation. So as you can see, it's quite broad range of masses where the relaxon can also explain dark matter. Yeah.
Stationary scale is 10 to the 90 to get a Hubble parameter of 0.1 or so.
Yeah.
And you don't take it over 100 G.
Yeah.
Then how do you make values? Then make dark matter, but how do you make ordinary matter? I think that's more important.
Yeah, I would hope that there is another mechanism which will do this work, but yeah, so we don't discuss this here. But as I said, I mean, so the more generic scenario for high reheating temperature is this black region. So I agree that this one is a bit less straightforward, but we also have significant region where we don't have to worry about the reheating temperature. Yeah. But yeah, that's a good point. Also, baryon generation of baryons asymmetry. Yeah, I'm not sure how to do in that case. Yeah, this is just the same in mass versus decay constant plane. Of course, the relaxon is also expected to have the usual couplings to FF dual. However, since they are model dependent, I don't show them here. But in principle, as you can see, yeah, so it also can live in a wide range of the parameter space. Yeah. Okay, so to summarize the talk, so I hope I provided interesting perspectives into the mechanism, and especially the role of fluctuations can be important and lead to this kind of interesting stochastic effects. Yeah, as you also saw, the relaxon mechanism can address several problems at the same time, which makes it interesting. And of course, in the future, it's important to study what other probes or observational signatures can be found to distinguish this scenario or identify this relaxon scenario. And with this, thank you very much for your attention.
Quite a few through. Any from the Zoom? Do we see any questions from the Zoom?
Thanks. So yeah, you mentioned addressing multiple problems at the same time. You know, can we really think of this as a potential solution to the strong CP problem when it seems like the amount of structure and organization is required is maybe worse than the tuning of the initial problem?
So there are two levels, I think. So one is, I mean, the relaxon mechanism itself is addressing another problem. So, okay, you can say it has many ingredients. You have to add many degrees of freedom to get this potential. Yeah, that's one thing. But the modification that one has to do on top of this to address the strong CP problem, I think this is really a very small. So essentially, there is no additional requirement in the setup. It's just essentially fixing the value of the Hubble scale will do the work. And I mean, it's not that we're tuning the Hubble scale to some value, but rather it's
it's kind of like to me, at least, it feels like just tuning of another name, in the sense that you're organizing the whole theory in such a way as to produce this very tailored outcome. You maybe don't have any very finely tuned parameters, but the overall structure is tuned.
I slightly, I'm not sure that I can agree with this because, as I said, I mean, we are not tuning a parameter compared to its nature. I mean, we don't have expectation for the Hubble scale, I would think, in compared to the theta angle, for example, which one would expect to be order 1. So I think it's much softer tuning than in my opinion. Yeah,
Okay. Maybe it's an issue of taste.
but it's a good point. Yeah.
Okay. Oh, here we are. Let's see. Why is the left side of potential linear and not
quadratic.
for disappeared?
Yeah.
You got the question. Repeat the question.
I think the question was why the left side of the potential is linear and not quadratic. So yeah, as I already mentioned, I mean the fact that that one uses a linear potential, there is no deep meaning in it. It's just the leading order term in the Taylor expansion near that particular point where the Higgs mass changes its sign. So it's not the statement is not that the full potential is linear, of course. It can have arbitrary shape, but of course we would expect that if it has a non-zero slope, then in the vicinity of that part of the potential, one can keep just the linear term. And I mean, if one adds higher order terms, this will not change the predictions. Maybe I'm not sure if this will further confuse or not, but so in principle, if one thinks of how to generate this this potential, and this is also what I mentioned before. Essentially, this linear slope is just a part of a larger cosine term with a very large decay constant, which can be obtained by mixing many axions. So if one looks at this expression here, so this one can think. I would say the potential actually looks like this. So this is the back reaction part, which is the cosine. And this is actually what I represented as a linear, but it's just the cosine with a much larger decay constant. So we need to have two cosine modulations with one having a much larger decay constant than the other one. And this can be achieved by this clockwork mechanism, mixing different axions. And then, of course, yeah, one can approximate this as linear in the region of interest. That's it, yeah. And this is the part where the Relaxion couples to the Higgs word. So. Yeah. Yes.
Yeah, thank you for the talk. I think that the thing that you have, there's still hierarchical parameters in the theory that creates the thing that there is a unit. Presumably, what you want to do say is that if you are not ignorant and you want to write down where those dimension full parameters come from, you still can maintain that it's the technical naturalness, right? To shield from the radiative correction. So you don't think why this, there is a hierarchy at the tree level between the parameters as soon as you can maintain the technical naturalness and the radiative.
Yeah, exactly. Yeah.
Is that the philosophy?
I would say so. Yeah. So yeah. Yeah, exactly.
What sets the initial condition of the relaxation? Why is it up on top of the hill?
Okay. So that's what one has to assume, that it starts somewhere on top of the hill. I mean,
it's very, very weakly covered, so it could be anywhere.
It could be anywhere, but of course, with the, let's say, 50% probability, it could be in the upper half of the potential, and that's enough. So it doesn't have to be at the top, but it just has to be before the mu h equals 0 point. So it has to be in the region where the Higgs mass is positive.
So you're saying its evolution is basically controlled by Hub and drag, and it's
Yeah.
going towards the required desired minimum point.
Yeah.
Solve your problems.
Yeah, independent of where it starts with. Yeah, as long as yeah.
But supposing it started, say, very close to where you wanted it to end up.
Yeah.
Why can't it just fluctuate away by the same argument?
Yeah, so one has to make sure that the fluctuations are not strong enough to bring it further down, I would say. I mean, it's or up. And this is.
So is it fair to say half the time you get what you want, the other half of the time you can't?
Yeah.
somewhere else and not solve your problem.
No. I mean, half of the time I get what one will get what we want. The other half of the time it will be or in the lower part of the potential,
Which is
and
not to satisfy you.
yeah, it will not go up. I would say. Yeah. So we solve it only in 50%.
You solve half the universe.
Yeah.
It's quite a bit.
Yeah. I mean, yeah. That's yeah. Exactly.
I haven't solved any.
Yeah. So.
Regular question.
Okay, so but I can read the question. So thank you. I have another question. Is there any idea already in which minimum we are in our universe or any constraints on this? Well, I mean, so what we know is the value of the Higgs wave, right? So this determines the barrier height in our minimum. That's the only information that we know. And we know that the theta bar is less than 10 to the minus 10. So it cannot be a very shallow minimum. But the rest, I mean, there are free parameters in this. If we trust this model, then it has some free parameters and they are not fixed. So yeah, for example, the slope. Yes. Sorry, time variation from what?
Time variation of fundamental constant.
Of the Hubble parameter. No.
The GF. G firm is changing.
So the Higgs mass is changing, but what effect are you talking about? I'm not sure.
Right, the value expectation value of the Higgs, is that changing with time?
Yeah. Okay. I think I understand the question. Yeah. So of course, as the Relaxion moves, once it's in the region where the mass squared is negative, the Higgs will develop a wave, and as it moves further, also the wave will change. But we assume that usually the Higgs is heavier than the Relaxion, so it much quicker adjusts to the new minimum. So essentially, we integrate it out, so it tracks the minimum at that time. Yeah.
Great. Thank you, speaker.